Welcome back to Acids and Bases and Salts. In part 4 of this unit, we're going to be talking about weak acids and bases, whereas before we had been talking about only strong acids and bases. I hope you have your calculator ready. Let's get started. Okay, so since weak acids and bases do not completely dissociate in water, their reactants are in equilibrium with their products. This means that the equilibrium constant, or K, is used to determine the concentrations of the reactants and products. We have Ka and Kb, which stand for the acid and base dissociation constants, respectively. Remember that water will not be included in the equilibrium expression because it is a pure liquid, and liquids are ignored. So we have Ka for acids, Kb for bases. Let's see how we can apply this. First, we're going to complete the equation and write the correct Ka or Kb expression. These equations at this point should be becoming familiar to you. HNO2 is H3O plus and NO2 minus. You should be able to do these equations very, very quickly without a whole lot of thought. So what's new here is the equilibrium constant expression, that's the K. In this reaction, NH3 is a base because it accepts a hydrogen, so this will be Kb instead of Ka. And its products, NH4 plus times OH minus, divided by reactants. Ignore water completely because it's a pure liquid. So the only reactant that really matters to us is the NH3. So that is your equilibrium constant expression, or your base dissociation constant expression for NH3. So let's look at HNO2. This will be Ka because HNO2 is an acid since it donates a hydrogen and it produces H3O plus. Products, H3O plus times NO2 minus, divided by reactants, HNO2, completely ignoring water as if it were not there. So that's how you're going to write your equilibrium constant expressions for acids and bases. Let's look at the math next. First of all, I have a typo on my screen, so ignore what's under the purple. Ka and Kb values give an indication to the degree to which a reaction proceeds. The larger the value of Ka, so that means it's a smaller negative exponent, the stronger the acid, the further the reaction will go to completion. The larger the value of Kb, the stronger the base. So large Ka, strong acid, large Kb, strong base. Strong acids and bases do not have Ka and Kb values because their reactions do go to completion, so they're not in equilibrium. Technically, the Ka or Kb values would be approaching infinity because there are completely products and no reactants. For a conjugate acid and base pair, the Ka and Kb values are related in the same way that H3O plus and OH minus are related in pure water. That is, if you multiply Ka times Kb, you get 1 times 10 to the negative 14. So notice that there is a chart on the back page of your notes that has a list of Ka and Kb values, and we're going to look at this relationship when we look at that chart. So turn now and let's look at that chart. So here's a small sampling of what's on that chart. Notice we have a whole list of acids, and the acid formula, and their Ka values. Also notice that a conjugate acid-base pair would be like HSO4 minus and SO4 minus 2, related by the loss of one hydrogen, or HF and F minus. That's a conjugate acid-base pair because they only have a hydrogen difference between them. So then also notice that the Ka and Kb values multiply to equal 1 times 10 to the negative 14. So 7 times 10 to the negative 4 times 1.4 times 10 to the negative 11 will give you 1 times 10 to the negative 14. Or 1.2 times 10 to the negative 2 times 8.3 times 10 to the negative 13 will give you 1 times 10 to the negative 14. This is really useful when you're given a Ka but you need a Kb, just the same way as if you're given H3O plus and you need OH minus. So you just need to memorize that relationship between. And so then these acids and their conjugate bases, or these are the bases and their conjugate acids. So while we're looking at this chart, I'm going to go ahead and skip ahead, and I see that the next question, find the pH of a 1MHC2H3O2 solution, is acetic acid. That's right here. And so it has a Ka value of 1.8 times 10 to the negative 5. So just note that. I'm going to come back to that for our next problem. And actually, let's look at the next problem. I'm going to write that Ka value down right here. 1.8 times 10 to the negative 5. Okay, so here is a weak acid problem. Find the pH of a 1 molar HC2H3O2 solution. So this is acetic acid. And we'll mix it with water. And really, any acid mixed with water is going to donate its proton to water. So water will become H3O+, and acetic acid will come C2H3O2-. So if HC2H3O2 is 1 molar, then we have to figure out the H3O+ so that we can figure out the pH. The problem is, since this reaction is in equilibrium, not all of that 1 molar will turn into H3O+ and C2H3O2- like it did for strong acids and bases. Only some of it will. So an icebox is needed. Initially, there's 1 molar acetic acid and 0 H3O+ and 0 acetate. But then it's going to undergo a change when the acetic acid will lose X and the products will each gain X because it's a 1-to-1 ratio. So that at equilibrium, we'll have 1 minus X and X and X. And then we're going to plug it into the K expression that we just practiced writing. This will be Ka, because acetic acid is an acid, H3O+ times C2H3O2- divided by HC2H3O2, completely ignoring water as if it weren't there. And now we're going to plug in the numbers that we know. 1.8 times 10 to the negative 5 is equal to X times X divided by 1 minus X. Now if you're looking at that, hopefully you notice that that's going to end up with an X squared term and an X term and a no X term, which means quadratic equation. This will be really tricky. So there's a shortcut. We can say that since the X is going to be pretty small, because the acetic acid doesn't ionize very well because it's weak, 1 minus X is approximately equal to 1. So that this becomes approximately equal to X squared over 1 instead of 1 minus X. That's going to make the math a whole lot simpler. I'll tell you in a minute how we're going to decide whether or not the X is negligible, but for now we're just going to treat X as if it doesn't matter, as if it's small enough. So 1.8 times 10 to the negative 5 times 1 is 1.8 times 10 to the negative 5. That's equal to X squared. Take the square root of both sides. X is equal to 4.24 times 10. Hold on, make that prettier. To the negative 3. 4.24 times 10 to the negative 3. So now that X is your H3O+. So then to find your pH, you take the negative log of your H3O+. And since that's a negative 3, this will be 2.4. And that is your pH. Next we have the percentage ionization. From the same problem, find the percentage ionization. So we know that initially the acetic acid was 1, but then the X that it lost was 4.24 times 10 to the negative 3rd. So if I want the percentage, I want the part that it dissociated out of the whole, the original 1, times 100. 4.24 times 10 to the negative 3rd divided by 1 times 100 gives you 0.424% ionized. Now earlier we said that X was negligible, which means X doesn't really matter compared to 1. But how do you decide when X is negligible and when it's not? And in fact, it has to do right here with this percentage ionization. If this number is less than 5%, if the percentage ionization is less than 5, then X is negligible. So this means that X won't matter. This is actually called the 5% rule. If the number is really close to 5, then you'll have to just use your best judgment. But really, anything under 5 means X doesn't really matter. It's less than 5% of the original number. Anything over 5 means that you should really go back and use the whole quadratic equation to solve the whole problem. Let's look at the next one. So the next problem deals with nitrous acid HNO2. So you're looking on your chart for nitrous acid HNO2. And it has a Ka value of 4.5 times 10 to the negative 4. I'm just going to go ahead and mark that and note it just so I'm sure I'm going to need it here in just a minute. Ka was 4.5 times 10 to the negative 4 for nitrous acid. So find the concentrations of the various species present in a 0.1 molar solution of nitrous acid HNO2, and what's the pH of this solution. So we're going to write a reaction. This time I'm going to write it without water, just because I want you to be able to see it with water and without, and be able to write it with water and without. It could go either way, and they both mean the same thing. We're going to use the icebox just like we did before. This is a 0.1 molar solution. This is going to lose some amount X. The other guys start at 0 and they're going to gain some amount X. We'll have a Ka expression because H plus indicates an acid. H plus times NO2 minus over HNO2. So we have 4.5 times 10 to the negative 4 that I got off the chart on the back. X times X divided by, and again, I'm going to try this approximation to see if that works out for me. I hope that it does, because that'll make my math a whole lot simpler. So 4.5 times 10 to the negative 4 times 0.1, take the square root, I end up with X is equal to 0.0067. To ensure that that X really was negligible, I'm going to find the percent ionization, which involves taking that 0.0067, dividing it by the original, times 100, and I end up with, oh dear, 6.7%, which is greater than 5%, which means the X is not negligible. I cannot make an approximation. This will not work. I suggest, instead of erasing this on your paper, that you just work it out in a different space. So what we have to go back and do is say 0.1 minus X and include that X. And now I'm going to have to solve it with that. So I'm going to distribute the 4.5 times 10 to the negative 4 into that term. So this is 4.5 times 10 to the negative 5 minus 4.5 times 10 to the negative 4x equals x squared. So if I put everything on the same side, 0 equals x squared plus 4.5 times 10 to the negative 4 minus x. 4.5 times 10 to the negative 5. Quadratic equation, here we come. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. A is equal to 1, b is equal to 4.5 times 10 to the negative 4, and c is equal to negative 4.5 times 10 to the negative 5. A, B, C. So I'm going to leave it up to you to solve that, to plug in those numbers, and you're going to get x is equal to 0.00649 or negative 0.00693. A negative number will give you a negative concentration, which is not possible. So there's your x. Remember, x is equal to H plus. So if I want to find the pH, pH is the negative log of H plus, which is 0.00649, which gives you 2.19 for your pH. And that's not the only thing the question is asking for. It's also asking for the concentration of HNO2 and NO2 minus and H3O plus. So HNO2, that's 0.1. And then the minus x really does matter because it's greater than 5%. So minus 6.49 times 10 to the negative third. So HNO2 comes out to 0.0935. The H plus and the NO2 minus, hold on, I'm trying to make that a pretty decimal there. The H plus and the NO2 minus are both represented by X, so these guys are both 0.00649. And I think that should be it. Let's look at the next problem. All right, let's work another little bit of a different problem. A 0.05 molar acetic acid solution is 1.9% ionized at 25 degrees. This time we're going to calculate the Ka. So we'll start with the equation. Always start with the equation. HC2H3O2 and water. So the HC2H3O2, the acetic acid, will donate a hydrogen to the water to give you H3O plus and C2H3O2 minus. This is 0.05. And then here's where I would say that minus some amount x plus x plus x, except that I know that it's 1.9% ionized. So it's actually going to subtract 1.9% of 0.05. So I'm going to have to figure out what 1.9% of 0.05 is. So 1.9% is 0.019. And if 0.05 was the whole, what is the part going to be? Let me make that 5 a little prettier. So 0.019 times 0.05, x is equal to 9.5 times 10 to the negative 4. So that x is the amount that's lost out of the 0.05, which means 0.05 minus 1.9% will really be 0.05 minus 9.5 times 10 to the negative 4. Since this is less than 5%, that's really the same thing. Let me make that better. As 0.05. But over here on the H3O plus side, 9.5 times 10 to the negative 4. And the acetate ion is also 9.5 times 10 to the negative 4. So now if I'm going to find Ka, A because it's an acid, H3O plus times C2H3O2 minus over HC2H3O2, plug in what I know, and that's 9.5 times 10 to the negative 4 squared over 0.05. If you would actually like to subtract the 9.5 times 10 to the negative 4, you can totally do that. And I end up with 1.8 times 10 to the negative 5. Which, if you check the Ka chart on the back of your paper, then this actually is the Ka for acetic acid. All right, we have one more problem left. I'm going to look at the chart first for my next problem. I'm kind of looking ahead just because that makes it easier for my video. This question is asking about the pH of NH3, that is ammonium. So I'm going to find NH3. Ooh, check that out. It is a base, not an acid, and it's got a Kb of 1.8 times 10 to the negative 5. So I'm just going to keep that in mind as I'm working in the next problem. Kb is 1.8 times 10 to the negative 5. So, what is the pH of a 0.05 molar solution of NH3, and what is the percentage ionization of NH3? So, NH3 and water. We just saw on that chart that NH3 is a base. Base means instead of donating hydrogen, it will accept a hydrogen. So NH4 plus and OH minus is what's left of water after it gives hydrogen to the NH3. This is 0.05 minus x plus x plus x. So it's going to be approximately equal to 0.05 if x were negligible. And since we have to find the percentage ionization, we'll figure that out here in just a second. Now we need the K expression. This will be Kb because NH3 is a base. So NH4 plus times OH minus divided by NH3. And the Kb, which we already looked up on the chart, 1.8 times 10 to the negative 5 is equal to x squared over 0.05. So we'll cross multiply and take the square root, and we end up with x is equal to 9.49 times 10 to the negative 4. So I'm going to take a pause right here, check the percent ionization, and then come back for the pH, just because I want to make sure I didn't need to use that quadratic equation. The percent ionization is the part over the whole, so that's the 9.49 times 10 to the negative 4, divided by the whole that I said that it was negligible against, that's the 0.05, times 100, and I end up with 1.9%. So there's my percentage ionization. It's also less than 5, which means my approximation there was valid. I am allowed to say that x is negligible. So now let me go back and say, what's the pH? So this 9.49 times 10 to the negative 4 is x, which means that this is OH minus. So when I take the negative log of 9.49 times 10 to the negative 4, and I get 3.02, what I'm actually getting here is the POH, not the pH. Let me make that prettier. POH equals 3.02. So if I want the pH, then I'm going to have to subtract that from 14. 14 minus 3.02 is 10.98. And there is your pH for this last weak acid problem. All right, join me again next time for polyprotic acids.